So Dania, so the final session is about parallel computing. Is Ulavidar online as well?
Yeah, I'm here.
Yes. So I might ask certain questions about the difference between Intel and OpenMPI, for example. So be ready.
Intel and OpenMPI is like apples and oranges. Yeah. Okay, I'm ready.
Yes. So considering the audience that we had and also the questions, and this example is very Python heavy. I'm not going to go into much detail about the code itself, but let's discuss the concepts instead. So I have this script that calculates. So I have uploaded this script to that link, Radovan, if somebody asks. Let's get the concepts first. So I have this small script that has a loop that goes 5 times and then sleep. So there were some questions about sleep on the HackMD. So this is just to hold the program, wait this much seconds. So it's going to go through a loop. It's going to start A first, sleep 3 because A is 3, 2 is B is 2, and 1. So let's run that and see how it runs. So it's starting A, the first A, and then after A is finished, it's B, B is finished C. It goes on like this 5 times. So this is sort of, we could say that this is like a serial thing. So one thing needs to end before the other thing starts. So although C is only 1 second, it ended at the end. But A is 3, but it ended, like it has to end before C starts. Something very small might have to wait a long time before something big ends. So the same thing, what I'm going to do is, let's see another file. You don't need to understand the content of the file. It's just I'm going to show the concepts. Instead of starting one after another, it's going to start all 3 at the same time and do it 5 times. Let's see how that works. So it started A, but C is finishing very quickly, if you can see, because C only takes 1 second. It doesn't have to wait A to finish. So this is kind of like not like a very one-to-one comparison of how the next example going to work, but more or less what you're going to show is, rather than doing things in serial, like you have to finish one thing before the next thing starts, when you have a lot of cores, for example, on our compute node, if you remember S-info node C123, for example, minus output cores. So we have 40 cores. So it can do 40 of these things simultaneously. But I think Ulavidar might talk later, like in his lecture, more about this course, and also Radovan later on. So instead of waiting for one thing to finish, we can ask many things to happen at the same time and then combine the results at the end. In addition to that, if you remember, we have a lot of nodes as well. S-info. So you have a lot of nodes. So you can recruit many of them to do the work. But not all of your programs might run across multiple nodes. So Ulavidar, what might be a reason that your program might not, you might be able to use multiple nodes?
This is true. There are not all problems that can be partitioned into pieces that can be handled independently. So the concept of parallel computing is that you can partition your problem so that each little piece will be handled by a separate processor or or thread, and then you put them together in the end. And not all problems fit that paradigm, but for well-structured problem, which is mostly in HPC, we are lucky, so it can be done. But there is a number of problems that cannot be dealt with in that way.
Thank you. That gives a very good entry point to this example that we're going to talk about.
And Sabry, there
yes.
is a hand raised. Ahmed.
Yeah.
Yes, thank you, Daniel. Thank you, Sabry, and thank you, Ole, for your introduction to the scientific computing parallelization concept. What I'm seeing here, like you didn't mention anything about like the dependencies between those A jobs, B jobs, and C jobs. Like, was there any dependencies, or like you were just running them parallel and no dependencies between them?
No. So there's no dependency at all. So it doesn't exactly, as I briefly mentioned, fit the concept of what we're going to mention here. But it's so that example is just take it as if you do things, if you do multiple things that can be done at the same time parallelly, it would be more efficient than if you do one after another, the serial way.
I just want to add that the jobs you saw, they are an example of a category parallel jobs called embarrassingly parallel. There are no dependency whatsoever between the jobs. And there is a whole big class of scientific simulations called Monte Carlo simulation, where each draw, you draw balls from a basket and look at the number, and you run a function according to that. And you can pull as many balls as you like and run as many functions as you like, totally independent of each other. And then when you're done with all the functions, you can do some reduction or something to find the smallest and the biggest, or sort them or whatever. So this is, he was touching on a very, very nice class of problems, because these problems that he showed you here with the sleep, you can run millions of them in parallel. So this is a very, very nice class of problems.
Yeah, thank you.
Yeah, but in the reality, you might want to combine results. So there might be some dependency in reality, but Ulla explained that very well. So here, what we're going to calculate is the value of pi. As I said, this is very Python heavy, and I'm not going to go into the code. So what we're going to do is we're going to throw darts. Right, we're going to generate random points like dots inside a unit square, and see how many of them fall inside the circle. Right. So using this information, let's say if we throw 100 darts, if 60 of them fall inside the circle, then we can use that information to sort of estimate pi. Pi could be this value. If you have more like understanding of these concepts and Python, all the details are here, but I'm not going to go deep into details. What I'm going to do is I'm going to run this without the message passing interface, and with the message passing interface to show this some slight differences in a very, very superficial way. The code which is used for this is there in the link that I shared in the beginning. If you can't find it, please ask in the HackMD and somebody will mention it. It's on the top in the scripts GitHub page. Okay, let's go to the concept a little bit. So the serial solutions, so they're using this NumPy library, which I'm not going to mention much about. Then it's going to create some random point. So it's also depends on how well your system is creating a random numbers, and it's do some slightly heavy calculations here to get some values. Then it calculates pi. So all these things you don't like if you understand it, please go through it, and then you may ask questions even. Only thing I'm going to show is how much time it would take to do this. So what I did was I combined all these blocks into one file so you can run it. First, I'm going to run it. I'm going to see whether there are any modules. If you remember in the beginning, I said we need some modules in order to run. So I have some R loaded. This is not where I want to be. I'm going to module purge, remove all the modules, module list, make sure that there are no modules loaded. I'm going to clear my screen, and I'm going to run this Python without loading any modules or worrying anything about it. I'm going to run this. Then it will complain. It's okay. So it's actually not the error I was anticipating that it will complain that it doesn't have NumPy installed, but it says that index error list out of range. Okay, let's see. Okay, maybe I have some NumPy installed. But what I'm going to do is I'm going to load a module with all these things included. For that, I'm going to use a module called sci-fi bundle. Let's
Sorry, Sabry, is that like you're supposed to put like an in samples like as an input to this Python script?
Yeah, very good point. Actually it has a index, isn't it, here? Yeah. So let's try that. 10. Okay, it actually runs. So I'm going to, I think I have NumPy installed in this. So I was I'm going to remove my NumPy and come back to you because I want to show the exact error. Okay. That's my terminal. Yeah. Okay. Regardless of that, I'm going to see the module. So when you are running this, if not like if you have not installed this NumPy, for example, locally, you'll get an error that I should have got. So I should have tested that before. You should load a module called sci-fi module avail. So I'm going to load this module. So you should have done this first. Unfortunately, I couldn't demonstrate that error. Then run this code. Right. Yes. Because I'm going to run this because it's a very like it finishes very quickly. But I'm going to get interactive node with about 4 GB of memory with this account for 50 minutes to do this calculation. Yes, I'm in the right place. I want to show you something more. So if you had loaded a module in the after you logged in, when you go to interactive node, you carry that environment. So you have to make sure that even when you're submitting a job, it's better to clear the environment before you load anything else. Here I'm going to run this Python program again. Let's say which Python. Okay. With about 100 random points. So as you see, if you know the exact value of pi, you would see that it's not that accurate, but you see that it used like fraction of memory, and it took this time. If I make it 10,000 points, then it will take a little more time, but the value will be more accurate. It takes more memory, and then it takes more time as well. So when this goes on like this, let's say if I want very large number of points, then what will take is, yes, it will, the value will be more accurate, but then we need a lot of memory and we have to wait a lot of time. So in order to like counter that, we're going to introduce something called this message passing interface, using by importing a certain Python module that I'm not going to go into details. So all that job scripts, for example, are here that if you want to run. So I demonstrated that here with the interactive node. But if you want to run it as a job and test it for 10 million, 100 million random points as a job, which will take some time, you could try this job. Okay. Let's see what MPI is. So the message parting interface is a set of tools which allow multiple parallel jobs to communicate with each other. So instead of running 100 million random numbers in one go, you divide the task into like 4, 5, maybe 100 partitions, and then run them independently, and then combine the results. Is there a better way to explain that, Olavidar?
No, I think you are spot on. There is only one thing that when you bring up the concept of MPI, is that this is a key thing with MPI, contrary to all other way of doing parallel processing. Each MPI rank you launch is totally independent of all the others. They do not know about each other. The only thing it knows is that there is a certain number of ranks in total, and I am rank this and this. And it's generally common to have the 0 rank called as master rank, but it doesn't really matter. It could be anywhere. So all ranks are totally independent of each other. They could be on totally different machines, which they often are. And the only way they can communicate with each other is by sending a message from one rank to another rank.
So for people who has a little more idea about these things, is it correct to say a copy of all variables are there in all ranks, or is it not? Like if you define a variable somewhere, all the ranks would know about it, or is
no?
It not?
If you define a variable in rank 0, if you put it into the source code, then of course all the source codes are identical. So any variables you declare and set a fixed number in the source code will be carried, because the same executable is run on every rank. But if you update a variable in one rank, all the others are not updated. So then you need to either communicate, have a loop and communicate that one to all the other ranks, or use a collective operation that operates on many rank at the same time. So it's remember that they are all independent. So any variable that you update are only updated on your local rank.
So we're going to use something MPI for 5 for this. Let's see this diagram. So this is what we did in the the first exercise. So here the sample number is, I think it's only 1024. Everything on one go, like as a single process. Instead of what they're going to do here is divide it into 4 chunks, 256 samples each, and then define 3 more additional processes here, and then delegate the, as Ulla said, the rank 0 is sort of like the controller or a master sort of task. It sends 256 each for, it delegates that task for each rank. Or is there another word for rank, Ulla, something that?
No, rank is it's a word you have to learn. So in
Learn.
MPI, there are ranks named from 0 to n-1. Yep.
Then, so each of these ranks would do the calculations all by themselves. And then at the end, it will combine the results, and it will, the rank 0, all the ranks would send the final results to rank 0. And then at the end, rank 0 would determine the pi. So let's say this this combination, so dividing the jobs, dividing that job into chunks, sending them to ranks, collecting the results back, and doing the final calculation takes about 1 hour, right? So that means we have sort of like a, no, 1 hour is a very, very bad thing. Let's say 10 minutes. So this 10 minutes, so the, regardless of how many ranks you spawn, let's say even if you spawn 1000 ranks, your job will not go more than 10 minutes, because there's this overhead that we call it. Is that correctly said, Ulla?
Yeah, but you have to do everything yourself. There is no free lunch here. So the only help you can get is some kind of reduction operations, but that's collective operations. So it's something that you learn when you start learning MPI, and learning MPI takes a semester or so.
Yes. Okay, so as we don't have a semester today, I have this file created that would sort of, I can show you the file as well. So the PyMPI. So all that in the note with some comments are here, what it does. So in that diagram, if you remember, it splits, it sends, it collects, it calculates, everything is included in that. So let's see a job that we can use to submit this. Parallel. So I have a job here. So if you remember that I always used n task 1 beforehand. So this is, I'm using 4 tasks now with node equals 1. For MPIs, usually you would run in multiple nodes, but for this demonstration purposes, I'm going to do it on 1 node with 4 tasks just for the demonstration purposes. And I'm loading this module. So when you load this module, you would also use this MPI's facility that you need. Let's have a look at that one. That's the, okay. That's not Saga. I have Saga installed here. I want to keep the both terminals up. Module list, module load, so when you load this, you will see that there's a module that's loaded, sorry, module list that will help what we are going to do, which is the OpenMPI. So we have mainly two versions of this MPI. So if you use this first tool chain, the free and open source tool chain, you will end up with OpenMPI version here. But if you use, let's say, a module purge, module avail other versions, let's see what other versions you have. If you use Intel for module, for example, here, module load, it will load the Intel version. So I forgot to mention the early,
you launched the Intel toolchain with compiled with OpenMPI, so you have
correct.
to launch an I MPI.
Correct. I loaded the Intel, but with the open toolchain. I had to find the one with II. Here, this one would do, I think, with Intel MPI. Yes. So is there a like if someone need to like has the option to select any of these modules, Intel or OpenMPI, does it really matter? Can they just
it depends on what your fancy. So yeah, both are supported.
Both are supported. Then let's run this job. While that running the job, I will open that other terminal again to show you how it is processing. Saga. Okay, let me have a little bit of that what Radovan mentioned before. I need little more time.
Yeah, it's not so clear to me. Why do you sleep there? Can you explain that? Like why the sleep command?
Yes, that is to Radovan to get the compute node, so I could go into the compute node and issue a top command to show these ranks running.
But they will not be running until 45 seconds later.
Correct.
Okay, good.
So let's make it 35 then, because I need about 30. Okay, let's make it even 20. So I need some time in order to go and find the compute node and to log into that. Okay, there is interactive. Okay, I actually did that on an interactive node. So let's see. I submitted a job inside a job, so it really doesn't matter, but you should not do that. Okay, so this priority means that the queue manager has checked, and it sees that I need to wait a little bit in the queue in order to get this running. Let's see. Let's give it another 2-3 seconds. Let's see why it is so. I didn't ask for much resources. Let's see which account I used. So I asked for, okay, developer queue, correct reservation, but it's asking me to wait. Okay, let's wait another few seconds. So this you could expect if the cluster is very busy, that you don't find a free table like now it's started. So let me log into, if I can do there first, is C154 top me. Okay, so these are the jobs that running. If you look closely, after the sleep 35 finishes, it will start those 4 ranks and then do the calculation. So focus on this terminal if you can. So that 25 seconds is it's not doing anything. It's waiting until the that. Okay, so if you see that here there are 4 things came up and went. If you are watching closely. So that's the end of that job. And then let's see the results. I forgot how many random points I used for that. Let's see. It's not much. It's about 10 million, 100,000. Yeah, but I could have actually done it a little bit more even. Let's see the output file. You see the rank 1 generated 250,000 samples and so on. So the rank 0 also contributed with 250,000 in addition to doing that orchestration thing. And the pi value was more or less it's closer than before. It has also calculated some error and how much time it took, and it took about 22 megabytes for the sample. But this is a sort of like a very, very, very simplified example, but your job would be much bigger in real life. Anything else that I see, Ulla, here that I should mention?
No, this is okay. You see that there, one thing to see that the ranks are shuffled, so they don't come in the correct order. But apart from that, you can see how much memory you used and reading the tasks and so on, and memory stats and so on. So it's nice.
Yes. So you see that it took 44 seconds to calculate. It was very fast. So it was difficult to go for these values much details, but you would see that it would have done 4 times, not exactly 4 times, slightly less than 4 times the work than the clock time it has spent if it is a bigger job. Okay, is there any specific question that I should answer? Let's see the HackMD. Radhavan, is there anything that I missed?
Well, I think all questions answered. I don't see any. I don't think there are any questions that we need to raise here in Plenum.
There is a hand raised.
Yeah. Please go ahead.
Okay, I think it was hands down now.
What was that?
Hands down now, so I didn't see
Hands
that.
down. Okay. That's all I was going to mention today. If there's anything specific people would like to ask or clarify, me or one of our colleagues could help. Otherwise, when is the next break, Dania?
12. It was
Yes.
supposed to be 12, but we can take questions if you have.
Mm.
Yeah, I see Ahmad has raised hand now.
Go ahead.
Was it unintentional, Ahmad, or no? It's hands down now.
Okay, so
Hello?
maybe someone exciting.
You hear me now, guys?
Yeah.
I'm sorry about that. I think it's like the microphone thing. Thank you, Sabry, and thank you, Ola, for the commenting on those parallel example, MPI example, and one thing that I wanted to see you, Sabry, doing it was using the same number of points in the serial script just to compare how much benefit we got from the parallelization.
Yeah, we can just run that job until let me make it a little bigger so it will make more sense. 100 million maybe. Let's see, 1000 here. Yeah, 100 million. I'll use the same number on the parallel as well. So on the one more thing, when we do things on the HPC system is you can submit as many jobs as you want, and it'll wait and it'll execute when it is appropriate. So you don't have to wait until one job is finished in order to submit another one. So I'll submit both. But I must warn you that for that benchmarking, this job is too small to get a very good idea of this, what we're going to explain here. So, SQ. So both, okay, one job has already finished, now the parallel one is running.
No, I don't think, I think you type batch instead of S batch.
For the serial, okay.
No, for the parallel
one, okay. S, okay, thank you, yes. I wrote it wrong. I did the parallel one and then the serial one did, okay, let's see this job. Oops. That's not supposed to happen. Serial is out of memory. Okay, let's see what it is. Three GB is not enough. Maybe for that many points, it was not enough memory. Let's see this one, parallel one. That's pending. Okay, so until that, oh, did I submit two serial ones? Okay, maybe the name. Sorry about that. So I have used the same name here. So if you see that the job name, I should have mentioned this one as a serial parallel one. So MPI. If I had done that, it would be more clear on the job script on the SQ. So it's a good example to show that using a proper name is very important. At the moment, one parallel and one serial is running, but I used the wrong name in one of those. Now let's see the output of that. Anything else that we want to try?
One of my favorite topics is scaling. Try one with 8 and see if we can get that running before the end of the session.
So what I'm going to do is I'm going to supply 8 tasks, And here the SRun would figure out that it does 8 tasks. Isn't it, Ole, that I don't have to mention it maybe?
No, you don't have to mention it. Slurm takes care of all of this for us.
Yeah, let's see whether there anything already finished. Okay, let's see this one. That is yeah, so this has calculated, because I used the wrong name. Now I couldn't figure out which one is okay. I can still, let's see. For the serial job, the job ID I got was dispatch serial was 431. This one. Okay, so there's another error here. So still it didn't have enough memory to complete. So this also proves a very good point here, that when you divide the job into smaller chunks, you don't have to rely on huge amount of memory. $16 maybe. Let's try that as well. Maybe Radwan, these things provide you a good platform for your efficiency lecture maybe.
Yeah, indeed. Thanks for that. Also, both Ole and me will come back to this tomorrow. And I think it's very, very important to, because today we learned how do we ask for X number of cores, but a completely different question is, so how many cores should we then use, and how much memory should we use? What is a good setting? And we will come back to that tomorrow.
Let's see the parallel one. 33,339. Yeah. Oh, it's not finished. Still pending. So this one is running now, the serial one still, the one with more memory. So I don't think this will finish. Maybe it will finish, but we can hang around for until 12. Until yeah. So please bring up any questions.
But just to mention the point about scaling now is that we take the time for the serial one, we take the time for the 4 one, we take the time for the 8 one, and we plot them into a diagram and plot the scaling. Ideally, it should be a straight line until infinity, but infinite number of ranks, but that's not normally the case. I'll touch upon this tomorrow. I'll go a little bit deeper into it, but this is how you actually do the scaling test. Issue a number of ranks or cores or whatever, if you're running OpenMP or anything in parallel, take the time for 1, 2, or 4 ranks or whatever, and then increase the number of ranks and do a plotting. Most of the times you will see that when you increase the rank to a certain number, it doesn't give any benefit. Then you have used too many ranks. So this is how you actually perform the scaling recording of the scaling data.
Very good point, Ola. So for this is how it would look like, the plot, if you do what you said that you probably show in your lecture.
And
yeah,
this is probably because of the context switching, Ole?
There's a whole bunch of things that affect scaling, but you should read up on Amdahl's law and Gustafsson's law.
Yes.
Especially Gustafsson's law, because if you increase the problem enough, then the scaling also increases. So if you run small problems, then it's harder to get scaling than with bigger problems. So read up on Amdahl's law and Gustafsson's law if you are interested in learning about parallel computing.
Yeah, thank you so much.
Okay, so I should have actually asked for more memory. So these jobs will not finish with the amount of memory I asked. Maybe the points were too large. Yeah, so I think I'll let Radovan and Olaf touch upon that later on. So there was one rank. So this is something that would happen when something that could happen in MPIs. One of the ranks actually fail during the processing, but at the end it will not make sense. So you have to give enough memory. And these examples, you could run it yourself and you can do a benchmark and see the code is here. You want to run it. And also in the GitHub, if you want to just download without typing the Python itself, it's in the HackMD on the top.
I can also upload a C version of this if some of you prefer C instead of Python. Because Python tend to encapsulate things a little bit. C is more bare metal than Python. So, but most young people prefer Python over C these days. So, but I'll forward a C program that can be uploaded to the GitHub, so you can play with C if you like to.
Okay, then that's all from me, Dania. Unless there's questions. You may take the screen.
Thank you, Sabry. It was an interesting session, and we will have a break now, and